So plant floor architecture is usually based on three main factors. So a controls engineer usually has the span of control. How much control am I going to have? Is it going to be an 8-cell robot, a 4-cell robot? How much control do I really need? The second thing is how many I/O points. Is it 100 I/O points or 400 I/O points? Number 3 is how fast do I need the data? So that determines the type of network and how many nodes I'd be using. This is a standard body shop in an automotive factory, and each section or each cell may contain up to 8 robots. So it would be an 8-robot cell, probably about 400 I/O points, and that would be a typical span of control. How many I/O points, and you need data updating at about every 20 milliseconds. That kind of governs the type of network you're using, how fast the data has to get there, and how big my system usually is. So if I look at a typical factory floor network, you have at the very top your backbone. That's in typically every manufacturing plant. And in the 3 blue boxes that you see underneath there are managed switches. A managed switch versus the standard switch that you can go out and buy at Best Buy would be these are managed switches, which means I manage the data. I only let certain amount of data go in and out. So if you look at this screen, as you see, there's 2 PLCs with I/O connected to them. And chances are, it's just like in that robot cell. Both have the same addresses. Them I/O robots would have the same I/O addresses. The I/O blocks would have the same addresses, so that way they could speed up their time in programming. But you don't want the information from one PLC to get to the other. So the information is blocked by the managed switch, so only lets certain information go between the 2 cells, like which model number is coming, or if another car is coming, or if there's an emergency stop. As you also look on that one address line, you can see that it's daisy-chained, and you can see the red blocks. The red blocks are safety blocks. Again, they're on that same network, so that's that safety and the standard I/O all being in the same network. The last block that you see at the lower left-hand side, it'd be an I/O link master. It's a single-point connection to a smart sensor. So this is a typical plant floor that you'll see in probably 99% of all the plants. Where we really see I/O link looking to be expanded is in that lower section. That I/O section is where we see the cost of the I/O architecture being greatly reduced by the expansion of I/O link. So if we look at the global trend through the IIoT history, or where we think smart factory really is going, is you have the development of smarter sensors. That happened in 2008 with I/O link that was developed by Siemens. Then you had SICK and Turk, IFM and Balluff developing these sensors. You had the PLC manufacturers, Siemens, Rockwell, and Mitsubishi starting to develop PLCs and software that would work with the I/O link. And now you have the manufacturers starting to use it, Hyundai, GM, BYD, and the tier 1 suppliers, MAG and KUKA, starting to use I/O link. But now you're starting to get to the leverage of I/O link output devices. And that's where we see a big expansion in using valve manifolds. The other thing we're starting to see is output devices with smart diagnostics. They're not dumb devices anymore. They have smarts that can tell you if I have a problem, or I can predict the problem. I can let you know, and it doesn't cost the customer downtime. So this is where we start to see this. Where does it fit in? Hardwiring had minimal cost, but you had minimal diagnostics. It's a hardwire. It's a dumb device. You had Ethernet, high-priced, smart, great performance, but you need something that was a little lower cost. That's why we think I/O link is really going to expand. You're adding diagnostics at a lower cost, and it's a similar performance at a lower cost. So if I look at this cost comparison over the life of it, you have on the left-hand side all our hardwired devices. Labor cost, very high. Component costs, very low. Then you moved into the field buses, where the component cost was very high, but the labor cost was low. So now you're looking at this open, decentralized type system that you'd have for I/O link, where we think it goes into a smarter factory because now you have smarter devices. So now you have that nice low-cost open architecture at a minimal component cost and a low labor cost.